Hey, welcome. So today we're going to talk about three words you probably use every day: work, energy, and power. But here's the catch. In the world of physics, they mean something incredibly specific, and it's probably not what you think. We're going to unpack the real science behind that feeling of effort we get every single day. So let me just ask you something. Are you feeling tired right now? Maybe you've had a long day of what you'd call hard work, right? Studying for an exam, thinking through a problem, maybe even just holding something heavy for a friend. But what if I told you that according to the laws of physics, a whole lot of that effort, it might not count as work at all? Get this. On the left, you've got a guy pushing against a wall with everything he's got. On the right, a girl is completely focused studying a book. Now, both of them are definitely using effort, right? You can feel the strain. But in the world of physics, nope. Neither one of them is actually doing any work. How on earth is that possible? Well, let's find out. And that is the big question, isn't it? When is work not actually work? We're going to break down the super strict scientific definition of that four-letter word and figure out why all that sweating and straining doesn't always make the cut. And here it is, the big golden rule. In physics, work has a really clear definition. A force has to be applied to an object, and, this is the important part, that object has to move. That's it. The key word is move. If nothing moves, then by definition, no work has been done. It's really that simple. So it really just boils down to two conditions, and you've got to have both. They're non-negotiable. First, you need a force, a push or a pull. And second, that force has to actually cause a change in position. The object has to go from here to there. If both of those things don't happen, it's not work. And this picture? It nails the point perfectly. This boy is clearly applying a ton of force. You can see the effort, but that giant stone, it isn't budging, not even an inch. So condition 1 is met, there's a force. But condition 2, nope, no movement. So the result? Absolutely zero work is being done. Or how about this classic example? You've got a porter holding a heavy load. Now, he's definitely applying a force, right? An upward force to fight against gravity and keep that luggage from falling. But if he's just standing still, there's no movement. So in the language of physics, no work is being done on the luggage. He's getting tired for sure, but the luggage isn't having any work done on it. But now, look at this. We've got a boy climbing stairs. He's applying a force to lift his own body up against gravity, and he is moving upwards, changing his position. You've got force, you've got movement. Boom. Now that's what physics calls work. So let's just nail this down. The really crucial point is that in physics, how you feel, your muscles burning, the sweat on your brow, that effort alone isn't enough. It doesn't count. There has to be motion. Okay, so if work requires motion, what is it that gives us the ability to make something move in the first place? Well, that brings us to our next big idea: energy. You can almost think of energy as the currency you have to spend to get any work done. And we're going to look at two main types: potential and kinetic. And the definition itself is just beautifully simple. Energy is the capacity to do work. That's it. If a system or an object has energy, that means it has the ability to apply a force and make something move. It's the fuel in the tank that you need to get things going. Now, this energy shows up in two main forms. First, you have potential energy. Think of this as stored up energy. Energy something has just because of where it is or its condition. Then you have kinetic energy, and that's the energy of actual motion. So a great way to think about potential energy is as ready-to-go energy. A stretched rubber band, a drawn bow, or the stone being held up high. None of them are moving yet, but they all have the potential to do work because energy has been stored inside them just waiting to be released. And this is what happens when all that potential energy gets unleashed. As that stone starts falling, its stored potential gets converted into kinetic energy, the energy of movement. And it's that kinetic energy that actually does the work of, well, in this case, breaking the window. So let's just put them side by side to make it super clear. Potential energy is the energy of position, like a stretched bowstring waiting. Kinetic energy is the energy of motion, like the arrow actually flying through the air. You could say potential is the setup and kinetic is the action. But here's where it gets really, really cool. These two types of energy, potential and kinetic, they aren't totally separate things. They are constantly changing into one another. So let's dive into what we're calling the great energy exchange. Now, this whole exchange is governed by one of the most fundamental rules of the entire universe, the law of conservation of energy. And what it basically says is you can't create or destroy energy. You can only change its form. So that stored potential energy, it turns into kinetic energy the moment it's put into action. A roller coaster is just the perfect example of this. Think about it. At the very top of that first huge hill, the car is barely moving. It is loaded with potential energy. But as it plummets down that drop, all that stored potential energy transforms into kinetic energy, and the car goes faster and faster. It's this beautiful trade-off. As your height goes down, your speed goes up, and then back again. And you see the exact same dance happening in a simple swinging pendulum. At the very top of its swing, it stops for just a tiny fraction of a second. That's all potential energy. Then, as it swoops through the bottom, it's at its absolute fastest point. That's all kinetic energy. It's just a constant, graceful conversion, back and forth, over and over. All right, so let's recap. We know work is a force that causes motion. We know energy is the ability to do that work. There's just one last piece to this puzzle: power. So let's put it all together. So what exactly is power? Well, power just adds the element of time into the equation. It's not just about if you do work, it's about how fast you do it. Power is the rate at which work gets done, or the rate at which energy gets used. And this is really the key thing to remember. Imagine two people lift the exact same box to the exact same shelf. They both did the same amount of work, right? But if one person did it in 5 seconds and the other took a full minute, the first person was way more powerful. It's all about how quickly you get the job done. So here's our final comparison. Energy, which we measure in joules, is like the total amount of fuel you have in your tank. Power, which we measure in watts, is how fast your engine is burning that fuel. You know, a 100-watt light bulb? That means it's using 100 joules of energy every single second it's on. So there you have it. Work is motion caused by a force. Energy is the capacity to do that work, and power is how fast you get it done. The crazy thing is, from the electrical energy in the device you're using right now turning into light and sound, to the chemical energy from your lunch allowing you to think, it's all just one big energy exchange. So I'll leave you with this to think about. What energy transformations are happening all around you, right at this very moment?